are doing tutorials, make sure you don't use Internet Explorer.
Right, you should.
Yeah, because that's a very bad browser. And
See, I'm not getting it.
Microsoft tried to rewrite the rules, and it didn't work. So,
Okay, thank you.
You want to write it down?
all right, let's go ahead and start with chapter 3. I'm going to talk about elements, compounds, and atomic structure.
Where's the?
Now, we've talked about matter and all the things that matter about it. Matter is composed of atoms. They're composed of protons, electrons, and neutrons. Protons are positive, electrons are negative, and neutrons, of course, are neutral. If you have the same number, your atom is a neutral atom. They live in the nucleus, and they're surrounded by the electrons. Modern atomic theory tends to describe electrons living in a cloud. The nucleus is very, very small. We'll actually talk about how that is determined today, or was determined. This represents a helium atom. We have 2 electrons in a cloud. We have 2 protons and 2 neutrons in the nucleus. Remember, the nucleus itself is teeny tiny in the middle, and by comparison, this is very, very large. We talked about atomic symbols. Remember, every atom, every element is characterized by an atomic number. The atomic number is the number of protons in its nucleus. The one thing that distinguishes one element from another is simply the number of protons in its nucleus. Doesn't matter how many electrons, how many neutrons, or whatever. Simply the number of protons. That's the atomic number. We said we could write an atomic symbol for every element. And the atomic symbol would contain 3 things. First, we would take the symbol for the element from the periodic table, so over here. As a superscript or subscript, we would put the atomic number. And as a superscript here, we would put the mass number. Now remember, the mass number was the number of protons plus neutrons, because those 2 together define the mass of the particular atom. Atomic number, again, is simply the number of protons. So you subtract those 2, you get the number of neutrons. If it's neutral, the number of protons, that's the atomic number, will equal the number of electrons. Last chapter, we talked about isotopes. We said that atoms exist with the same number of protons and with different numbers of neutrons. And so for carbon, for example, carbon-12 is the common isotope. 99% of all carbon is carbon-12. A little bit of carbon-13, about 1%, and then a tiny trace of carbon-14. These are all carbon. They just have different numbers of neutrons in their nucleus. Any questions? I'd like to expand the conversation here just a little bit and talk about subatomic particles and the concept of radioactivity. Now, later in the semester, we're going to do an entire chapter on radioactivity, so we'll review all of this. But this is just the concept of subatomic particles and radioactivity. Radioactivity was actually discovered many, many years ago. This is a plate from 1896. These guys were looking at phosphorescence. Phosphorescence is when things glow, okay? So they were looking at that, and as part of that, they used photographic plates. Now, in those days, photographic plates were a big deal because you had to take this gel with silver iodide, had to spread it very thinly over a glass plate, another plate on top. It had to be done totally in the dark. So it was a big deal to make these things. Well, somebody in the lab had prepared all these plates, and then somebody else came and put a little jar of a uranium salt on it. And when they went and developed it, right here in the middle was this big ugly splotch where the uranium was sitting. This is called fogging. Now, they had no clue what was going on at first, but they finally figured out that something from the uranium was causing these plates to go bad. When it turns out, this is Marie Curie and her friends, finally demonstrated that these uranium and radium salts were undergoing a decomposition of some sort. So the nucleus was expelling particles. These particles could be neutral, it's a gamma ray, or they could be charged. Uranium would kick out what was called an alpha particle. Now the alpha particle, if you recognize this little guy, is what we just saw for the helium nucleus. It has 2 protons and 2 neutrons. No electrons at all. But because it has 2 protons, it's a helium, right? It was just kicking this stuff out of the nucleus. You could also take the nucleus and you could kick out what was called a beta particle. Beta particle seemed to be an electron. It was negatively charged, had a very low mass, but it would just spit out of the nucleus. Gamma particles, as I said, were high energy photons, but they were neutral. So that's what Curie and her friends found. Alpha particles, turns out, are very, very low energy. If you have an alpha emitter, like uranium, a simple piece of paper will totally stop it. Beta particles are much more energetic. You need, like a little sheet of aluminum. It will just make it through aluminum foil. Gamma particles, extremely high energy. These guys can come clear across the entire universe and still hit here on Earth with a great deal of energy. They can go through brick walls, they can go through 10 centimeters of lead, very, very energetic particles. We measure these guys, and we'll actually get to play with a Geiger counter later. But we measure them with what's called a Geiger counter. A Geiger counter consists of a vacuum tube here. This is a vacuum in here. Very, very low concentration of a gas. And the idea is that one of these particles will come in through this window. It's a little micro window, actually. Will come in. And as it does, it ionizes this tiny trace of gas that's in there. Now you set up a high voltage between this little rod in the middle and the outside. So when the particle zips by, basically you get a spark that goes from here to there. And your electronics interprets that as a click. And that means a particle has entered. Like I say, we'll get to play with this a little bit later. Anytime you have an element that spontaneously undergoes decomposition in the nucleus, to emit alpha, beta, or gamma particles. We simply term that as radioactive. Now, alpha particles, like I said, are the lowest energy. You can stop them with a simple sheet of paper. Surprisingly, however, alpha particles are incredibly toxic. Plutonium, which you may have heard of, and polonium, which was in the news a few years ago, are extremely toxic elements. And the reason they're so toxic is that if you inhale, let's say, a piece of plutonium that is maybe 1/1000th the size of a grain of salt. So you're talking a microgram. You inhale that, it will go in your lung, and sitting here in your lung, it will emit these alpha particles. Alpha particles don't travel very far, but as far as they travel, they can be extremely damaging. And they basically just rip up your DNA. If I had a piece of plutonium the size of my little thingy here, this would poison the entire planet. It's just astounding how incredibly toxic these things are. Every fission weapon these days contains enough plutonium to poison the entire planet. Everyone on the planet, 100 times over. Every single bomb does. It's amazing. Well, uranium-238, this is the one that was originally formed in plates, is a classic alpha particle emitter. This is the atomic symbol for uranium-238. Mass number of 238, 92 protons, right down here in the periodic table. This will spit out an alpha particle. Now, when it does, it spits out 2 protons and 2 neutrons, doesn't it? That means that this element is no longer uranium because we've lost 2 protons from the nucleus. If we look at this equation, we go from uranium with an atomic number 92, is our alpha particle, and we made thorium. Thorium is right down here, 2 removed from uranium. So we make a new element. We also kick out 4 mass units. So this thing is now thorium-234. If you look at this equation, and we'll see this later when we do radioactivity, this is called a nuclear equation. Remember I said in the chemical equation, you had to have the same numbers and types of atoms on both sides. And the mass had to be the same on both sides. Well, the same thing for a nuclear equation. If you look at this, we start off with 92 protons. We wind up with 92 protons. We start off with 238 total mass units. We wind up with 238 mass units. We simply made 2 different elements out of it. We've reduced our mass by 4, so we're at 234. Our alpha particle has no electrons, so it has a charge of +2.
So that would be a chemical change?
This isn't.
Or would it have a physical change?
No, this doesn't fit into the physical or chemical change. We're actually transmutating one element into 2 others. Now, whenever you think of radioactivity, you think about, things that go boom, right? This is fission. It's the same process. The classic example of this is uranium-235. So again, we have 92 protons, but our mass number is 235. This is a very unstable nucleus. And if you take uranium-235 and you shoot a neutron at it, and if you're lucky, remember the nucleus is so tiny, but if you're lucky, the proton, or the neutron, I'm sorry, will hit the nucleus. So we go from 235 to 236. 236 is very unstable. Let's see if this works. Here it comes. Now we're at 236, and when that happens, it splits. When it splits, it evolves a huge amount of energy and releases 3 more neutrons. In terms of a nuclear equation, we would just show the 2 elements that it's split into. We don't show the energy, but there's a huge amount of energy released, and 3 high energy neutrons. Now the reason this is a fission chain reaction is that if you have a big enough wad of uranium-235, what happens is, remember we started this off with 1 neutron. Here we just split out 3 more. These 3 can each hit another uranium. So they split, and they each produce 3 more. And so the chain reaction goes on and on and on. The amount of energy yield is fantastic. Classic way to show that through this chain reaction is through the mousetrap demonstration. Now this is a room, these are all little mouse traps. And can you imagine somebody doing this for a living? Somebody sat back, set all these mouse traps, and put a ping pong ball on every one. Now we're going to show 1 ping pong ball being bounced in here. It'll hit something, set off the trap. And just like a chain reaction, suddenly everything in the room starts to go up. And that's how you get fission, and all the energy evolved from this is how you make a nuclear bomb. Again, later on, we'll actually talk about how to make one. Turns out it's so incredibly simple if you happen to have the stuff. But it is, it's just incredibly simple. Well, we talked about the odds of hitting the nucleus. These are tiny because the nucleus, like I said, is very, very tiny. Now, this is the little movie clip that we had when we started. This is early work from Rutherford, so probably in the late 1800s, where he was actually able to figure out how to measure the size of a nucleus. Now, this is an astounding feat, really. Once alpha particles had been discovered, and they were understood a little bit, what he did was he took a source, so a little chunk of uranium. This is a pinhole, it's a little tiny hole here. So you get a tiny, tiny beam of alpha particles coming through. Remember how we said gold was the most malleable of all metals? You can pound gold so it's literally just a couple atoms thick. He took one of these little bits of gold leaf and stuck it in this beam. What happened was, this alpha particle, which is positive, and this represents the nucleus of the gold atom, it's positive too. So as these came, they were repelled by the positive nucleus and they bounced off. And from his fluorescence detector, he could measure the angle that they bounced off. From this, he was able to determine that the nucleus in a gold atom was an incredible 10 to the minus 15th meters. So incredibly small. Like I said, if we had a golf ball in Wrigley Field, basically the field would be the electrons and the golf ball would be the nucleus. So it's a little tiny thing holding all the mass of the atom. Any question on the concepts there? Now on the exam, this is just going to be simple concept questions. Make sure you understand alpha particles. That are +2. Beta particles are -1. Gamma are neutral. And perhaps most importantly, that the nucleus is just so incredibly small within the atom. It's almost entirely empty space. Now these electrons that occupy all this space around this teeny tiny nucleus, we've said a couple times they live in a cloud. The cloud has various energy levels. These are referred to as quantum levels. Now, as we look at our periodic table, you note that this is numbered 1 through 7. Each of those numbers represents a quantum level. It's the energy level associated with the various electrons. Here's our numbers. The maximum number of electrons that can live in a quantum level is basically given by the equation 2n squared, where n is the level. So if we have level 1, 1 squared is still 1. 2 times 1, we can have 2 electrons in our first level. If n is 2, 2 times 2 is 4, times 2 is 8. We can have 8 electrons here. 18 electrons here, 32, and blah, 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 blah. Now within each of these quantum levels, the electrons exist in what are called orbitals. Orbitals have the names of s, p, d, and f. Now the s electrons occupy a sphere. They surround the nucleus in this cloud. So when I show the little cloud there, that kind of represents an S sphere. One orbital can only hold 2 electrons. Next to the S, we have the P's. Now the P's consist of 3, called P, X, Y, and Z. And again, each of these can only hold 2 electrons. Beyond these guys, it really gets kind of cute. This is the d orbital geometries. If you look at these, all of these little lobes, this one's my favorite. Got a little donut around the middle. Lobe, top, and bottom. This one's even more interesting. It has 2 donuts. These are the f orbitals. What an orbital is basically is just a region of space where this electron, or these electrons, can live. All of these exist simultaneously around a single nucleus. This is the same math that allows you to justify what's called the multiverse. You've probably heard of the notion of cosmology, where we exist in many, many parallel universes. Well, in that concept, each of these can be a separate total universe, all existing at once and totally separated from everything else. So it's the same sort of concept. Now, if you go back to your periodic table, again, why does it look so silly? Well, our first period can hold 2 electrons, that's it, right? We put 1 electron and we have a hydrogen. We fill up the 1s level and we're up to helium. So our 1s level is totally filled by the time we get to helium. Our level 2 here. The first 2 electrons are going to go into the s level. Again, this is a nice spherical thing. Remember, 2 can hold up to 8 electrons. So the other 6 go into these guys, and these are our p orbitals. Px, y, and z. And we put 2 electrons, 2 electrons, and 2 electrons. You can actually just count across. Nitrogen, for example, will have 2 electrons here in the 2s, and then 1, 2, 3 electrons in the p orbitals. Our third kind of looks like the second. We put 2 electrons here, then we're going to fill up these guys with our p's. It should have d orbitals. It turns out that these are slightly higher energy than the 4s level, so they fill later. We're not going to worry about this too much. But in the 4th level, we'll put 2 here. Then we'll fill up our d levels, here's my cute one. And then we'll fill up the p levels.
Are we supposed to know
Well, you'll see what we're, I hope you will understand why we have to do this introduction. First of all, I want you to understand why the periodic table looks so simple. Okay? As opposed to just a table. Number 2, we're going to talk in just a minute about the concept of valence. And it turns out that the electrons that are involved in valence, as bond forming, are going to be these guys, the highest energy electrons in the atom. Now in this course, we're only going to deal with the first 3 periods. So you don't have to worry about the D's and stuff like that. The first 3 periods are actually fairly simple. And I think you'll see that as we get to it.
I know, but are we supposed to know how many p orbitals?
Well,
are
you should know
each?
that there are 3 P's and that there's 1 S. Pretty much that's it. For every level, we will have an S. For our second level, we'll have 3 P's. Our third level, we'll have an S and 3 P's. Those are the things you need to know. There's a little bit more to it. Remember I said every orbital can only hold 2 electrons. Well, as you describe electrons mathematically in quantum mechanics, there's this number that comes across that's called spin. Now it's called spin. This shows electrons actually spinning. But they're not. They don't really spin. But they behave as if they do. When you take a spinning charge, it incites a magnetic field. And like any good magnet, it can be oriented up or down. In chemistry, we tend to use little arrows up and down to represent these electrons. Now, the reason that this is important is that when you put electrons into an orbital, they must be opposite spin. One up, one down. This is called Hund's rule. And basically it says that when you put electrons in orbitals, you're going to put them in one at a time, and then you're going to put them in so that they pair, but they must pair with opposite spins. So for hydrogen, right here, we have 1 electron we're dealing with, right? We would show this as the 1s electron. It's 1 because it's the first period. It's s because these are all the s electrons. And we have 1. So we will show this like that. 1 arrow up. Now you could show it 1 arrow down, but that'd be a downer. I always show up. Helium is also in the first period. So we're putting electrons into the s orbital again, but they must be opposite. So for helium, we would show it this way, 1 up and 1 down. We abbreviate this as 1s1 in the 1s orbital, so the first period, s orbital here, we have 1 electron. For helium, we have 1s2. So first period still, but now we fill both of these slots. Let's look at something a little more interesting. Let's do carbon. Carbon is over here in the second period, atomic number 6. It has 6 electrons. Now because it's in the second period, so it's here, that means that the first period is totally filled. We're full. It's all done. So the 1s is full. In the second period here, we're going to have 1, 2, 3, 4 electrons. First 2 are going to go in the s, and these are going to go in the p. So, we start off with our 1s, our first period, totally filled. Go down to the second period. First 2 electrons are going to go here. So that's our 2s, and it's full. Now we have 3 p orbitals. We have 2 electrons left, so that's 1, 2 electrons. Hund's rule tells us they go in one at a time with the same spin. And that's carbon. We have filled up the first period. That's the 1s. Starting here in our second, those 2 go into the 2s, and those 2 go into p orbitals.
Why
The
do you have
reason-
2s? Where did you get the 2s from?
Get the what?
The 2s.
The what? Squared 2?
2s. Yeah, the second row.
Again, that's just a shorthand. If we wanted to write this in shorthand notation, we would do it, well, this is the full configuration then. 1s has 2, 2s has 2, and the 2 p's have 2 more.
I know, but where does that shorthand?
Well, here's the shorthand. For the shorthand, what we do is we simply say, in the 1s, we have 2, that's those 2. In the 2s, we have 2 more. And the 2p, we have 2 more. The shorthand doesn't tell us their spins. It just tells us how many. Look at one more. I think it'll make sense. Let's do fluorine. Fluorine is also in the second period here, right? So because it's in the second period, right here, that means that the first one is totally full. So that's 2 electrons, right? Yeah.
This is the orbital rings, correct? The electrons
Right.
fall through the
But these are the orbitals. Orbitals are just these pieces of space where these things live.
So So aren't these rings of orbits on these things have certain amount that can be built on these?
Right, they can, each orbital can only hold two.
On each ring.
Yeah.
Ring.
Right.
So it isn't like two single T, it's only two.
Right, well, we have two up here. For fluorine, we have two in this one. Then we're down here, we have two in the S, two in the 2S, right? So this one's full. And we're gonna have 1, 2, 3, 4, 5 more p electrons. This is our p block here. This is the S block, the p block. All right. Atomic number 9, there's 9 electrons. 2 in level 1, 7 in the second. Okay? Total of 9. 1s, that's this guy, is all filled. Okay? 2s, that's this guy. It's filled too. And in the p orbitals, we have 1, 2, 3, 4, 5 electrons. Now remember, these go in one at a time. Then we pair them. And this is our total configuration. 1s is filled, 2s is filled, 5 electrons in the p block. And again, you can look at the periodic table and tell that. There's our p block here. 1, 2, 3, 4, 5.
How do you know to start with the up?
Oh, you don't. I always start with up. Because I'm optimistic.
What's the one in the middle called?
Oh, these guys in the middle? Well, they get very, very complicated. These are the d orbitals, and these are the f orbitals.
Oh,
So those are the D blocks.
Yeah, this is the d block, this is the f block.
So
You don't want to talk about
that.
Not yet.
The second, and 2p5 is
If you look at your periodic table, and I think this is probably the best slide to sum it up.
the should do this first.
Look at your periodic table here.
Oh.
Our first two here, this is our S block. Those guys there, those are S electrons. 2 electrons max. This is our P block over here, these guys. 6 electrons max. This would be D's, these would be F's. Don't worry about those. Way beyond this course. But just remember S and P.
So S is 2, P is 6.
S is 2, P is 6. They go in one at a time with the same spin, and then they pair up with opposite spins. All right, so let's look at something like sulfur. Sulfur's in our third period. Remember, our third period doesn't have D's. It does, but we don't count them. So let's look at sulfur. This is an exam question. Let's look at sulfur on our periodic table. It's right here, third period. All right, so what does this tell us?
3 S's.
It means one is full, isn't it? It actually means that 2 is totally full too. Totally full. And in 3, we have 2 in the 3s, and then we have 1, 2, 3, 4 in p's. So, from the shorthand nomenclature, which of these matches? We need the 1s with 2 electrons. Well, they all match. We need the 2s with 2 electrons. Again, they all match. We need the 2p with 6 electrons. And they're still the same. 3s, these guys, 2 electrons. Which one of these correctly describes sulfur?
See.
Yeah, we're in the P's, so it's 1, 2, 3, 4. And there it is. This is how the periodic table is organized. By how the electrons go in around the nucleus. Let's look at another one. How many s electrons would there be in beryllium? Well, beryllium is right there, it's a Be.
2.
You got it. The 1s is totally full, isn't it? So that's 2 of them. We're in our s block, and we have 2 more s electrons. Lithium, atomic number 3, right here. How many electrons are in the first shell? A little bit of a trick question, I suppose.
2, yeah.
Yeah, 2. The first shell is period 1. It's full. There are 2 electrons. All right, this one is cute. The numbers of pairs of electrons in an atom with this configuration would be what? We have 4 electrons in p orbitals, don't we?
4.
How many pairs can there be?
2.
Yeah, now 1 pair. Remember, they go in one at a time. Then you pair them up. So this is what it looks like. Here's our 2p4. We put 3 in, and they're all up. Then we put 1 more, and it's paired. We go in one at a time, with the same spin. Then you start to pair them. Yeah.
Why is
So
it?
if there's 4 electrons in the p orbital and a pair is equal to 2, why is it not 2 pairs if it's 4
Because
electrons?
remember, they don't pair up. They can only pair if they're opposite spins. And the rule says you have to put them all in with 1 spin, up or down. Then you put in opposite spins.
How do you know what spin is on it?
Doesn't matter. You can write it up, you can write it down.
So if I wanted to write 1 up and 1 down, why wouldn't I have 2 pairs?
That would be 2.
Well, no, because the rule says they all have to go in with the same spin first. So the first 3 all have to be either up or down.
This is the Kilo rule or
That's untrue.
the Hun rule?
I think there's one more question here.
That was a confusing one because I didn't get it. Because why couldn't you put,
I'll
like
go
you
back.
said, 1 up and 1 down?
You gotta put everything that spins at the same time, so everything up first.
Right.
And then you can put the ones that are going down.
You have to fill the 3
And
ups,
there's only 4.
and then you start with the downs.
But why wouldn't you fill 2 up and then 2 down?
You gotta
So
put
you have to fill them all.
up first.
They all have to go in, 1, 2, 3. Then you can do down, down, down. That's just Hun's rule. Hey, argue with him.
Where is he?
I don't get it.
All right, here's neon over here. How many s electrons are in the highest energy level? Well, remember I said as we go down the groups, the energy levels go up, don't they? So for neon, when you're in period 2, how many 2s electrons do we have? Right, this is our S block. It's full. 1, 2.
You don't have the top? So you don't.
No, no, because we're asking, the question says the highest energy level. All right, now on an exam, you're not gonna have to deal with a whole lot of this.
That's a lot of trick question.
You're not gonna have to deal with a whole lot of this on an exam. But the point of this is so that we can understand the concept of valence. Valence electrons, where we're going to be making bonds, are going to be the ones in the highest energy level. And that's why we have to know this. We have to be able to count, if we were dealing with carbon, at our highest energy level, that's the second period, we would have 1, 2, 3, 4 electrons. That's the concept that you need to come away with. Now there's a tutorial for this, of course. Some people have trouble with this. It's still worth 5 points if you can get it. But basically, what you do is you click on the problem, and it will do something like this. You can't put little arrows, obviously. So what I had this do was simply put a number. You're either going to put 2 or 1. Don't put 0, just 2 or 1. So for sulfur, if we were doing this for sulfur, here's our periodic table, and here's sulfur. How many do we have in the first period? 2. How many do we have in the 2s? We have 2 in the 2s. Remember, it can only hold 2. Our 2 p's here, this is totally full, isn't it? How many do we have? 1, 2, 3, 4, 5, 6. But they have to be paired 2 at a time. How many are in the 3s? That's these guys. That's 2. And now our 3 p's, we have 1, 2, 3, 4. So what do we put here? Remember, they're going to go in 1, 2, 3, and then 1 more here.
Just 2, 1, 1.
And we got it right. Lithium, how simple can you get? Lithium lives right up here. So our first level, how many? 2 electrons. Our second level, how many electrons? 1. Let's do 1 more. Silicon. Silicon is over here right under carbon. So it'll be right here. So our first level, 2. Our second level, 2 in the S. And all these P's are filled, aren't they? So that's 2, 2, 2. Our third level, we filled up these guys. That's 2. And how many in the P's? Only 2 electrons in the P's, right? But they have to go in one at a time. So we do it as 1, 1. Now, go ahead and try this tutorial. Once again, it's worth 5 points to you if you can get it. Sorry. We're back on the end, okay. So try it. Again, only 5 of them, and again, all the questions will only center on the first 3 periods. So no D's to worry about, and just see if you can master this concept. Now, I said a couple times, why is this concept important? Because electrons reside in 2 general areas. This is carbon. Again, carbon over here, second period. So our first period is full. We have 2 in the 2s and 2 in the 2p's. These electrons that are closest to the nucleus are called core electrons. And they don't do anything. They don't do anything. They just sit there. All right? Well, that's important too. But they just sit there. But these electrons that are in the second period, so the whole group that's in the second period, all 4, are called valence electrons. And these are the guys, the highest energy electrons. These are the guys that are going to make bonds. So when we make a compound, we're going to be dealing with only the valence electrons. If we were looking at fluorine, over here, it's in the second period. How many valence electrons? Just start counting at your second period. 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. And again, these are the ones that make bonds. Yeah.
Valence electrons are only going to be on the second period?
No. Well, for fluorine and carbon, all of the second period electrons are valence. All of them.
Only the second period.
Only the second period. First period is core. If we had aluminum, okay, the core electrons would be all the ones in periods 1 and 2. And aluminum would have 1, 2, 3 valence electrons.
In the third period?
In the third group here. So third period, third group, all of these are core. And these 3 right here would be valence. We'll get to that again in a second. In order to help with this concept, this guy named Lewis, in the late 1800s, figured out this valence electron stuff and came up with what he called the Lewis dot structure. In a Lewis dot structure, what you're going to do is simply take the symbol for the element and put the valence electrons around it. That's all you do. So we were dealing with carbon, right here. Carbon has how many valence electrons? 1, 2, 3, 4, right? So we start off by writing a C. Valence electrons are going to be those in the second level. And so we're going to put the valence electrons around the atom. Those are Lewis dots. Now the rule for Lewis dots is that you put the dots in one at a time. Then, if you have more than 4 valence electrons, you pair them up. So this is carbon. Let's do fluorine. For fluorine, we're over here, right here. We have 1, 2, 3, 4, 5, 6, 7 valence electrons, right? Start off with our F. Step 1, we put 4 electrons around one at a time. We have 3 more to add, don't we? So we do these, and we pair them up. Now, everybody wants to know, is this the way it has to look? Can my single electron be here, here, or here? Of course. It's simply bookkeeping. Simply bookkeeping. The only thing that's important is that we have 3 electrons that are paired and 1 that isn't. That is a Lewis dot structure. Now, Lewis dots are actually kind of neat because you can use them to explain the formation of charged elements, ions. You can also use them to explain covalent bonds. How do you know how many valence electrons? Remember I said that even though there are 18 of these things going across, that it was really handy just to number them 1 through 8? Well, if you hadn't noticed, the group number corresponds to the number of valence electrons, doesn't it? So up here in group 4, we have 4 valence electrons. Group 5, we have 5 of them, 6, 7, and 8. So the simple group numbers, 1 through 8, tell you right away how many valence electrons you're dealing with. Any questions? All right, let's take a simple Lewis structure and let's make an ion. Remember, an ion is something that has either too many electrons or too many protons. So it will either be plus or minus. When we want to make a Lewis structure of an ion, what we want to do is just put our valence electrons around, and then we're going to either add or subtract electrons. Let's do chlorine. Chlorine exists as a -1 ion. It's an anion. So step 1, we would draw our chlorine right here. Now it has 1, 2, 3, 4, 5, 6, 7, group 7, 7 valence electrons, right? So if we just drew the Lewis structure of chlorine, it would look like this. Now to make the chloride anion, that's 1 negative charge. All you do is bring in 1 more electron to pair it up.
Do you have to write that negative symbol on top? Do you have to write that negative symbol on top?
Yep, gotta write the charge, plus, minus, or whatever. Doesn't have to have a circle around it, I just always do that. Now, what has happened here? Chlorine has 7 valence electrons here in group 7. We've added one, right? This makes it look like it's a group 8. And remember what our group 8 was? We call those inert gases. So once we get that extra electron in, chloride acts like an inert gas. So we've gone effectively from chlorine here to the moral equivalent of argon. Once we fill up the shell, it acts like it's inert and it doesn't react anymore. Let's do another. You do this one. Sulfide dianion. Our sulfur is here. It's in group 6. So we're going to write our S. And we're going to put 6 valence electrons around it. Because there's 6, there are going to be 2 pairs and 2 singles. Now to make this a dianion, what do? Simply add 2 more. And we show this as a -2 ion.
2 minus, or does it matter where the minus is?
Some people write it 2 minus, some people write it -2. Nitride. Nitrogen is here in group 5. Symbol is N. And then we put 5 electrons around it. Because there's 5, we'll have 1 pair and 3 singles. And how do we make a trianion? We simply add 3 more electrons. Now we talked about sodium chloride, right? Sodium is a cation, isn't it? It's positive. Let's do the same thing here with sodium. Sodium, +1 charge. Here it is. It's in group 1. So it will have 1 electron more. We write our symbol. Group 1, so it has 1 electron. How do we make this positive? Well, we have to take that electron away, don't we? That means it'll have more protons than electrons, and it'll be positive. So we simply take this electron, and it goes away. And we're left with sodium cation. Now, I hope you've noticed what we've been doing here. We start off with elements that are somewhere here in the periodic table, and we're either removing electrons or adding electrons so that we get over here to group 8. For chlorine, chlorine was group 7. We added 1 electron, and that gave us the electron configuration of argon, which is group 8. For sulfur, we added 2 electrons. It's here in group 6. And once again, we move from here over to the configuration of argon. For sodium, we started here in group 3 and we took 1 electron away. When we did that, we moved from sodium up here backwards to neon. Once again, group 8. This is called the octet rule. And what we're going to strive to do is to build molecules such that the atoms, the nuclei, are surrounded by 8 electrons. That is the same as the inert gases, and that means that it's a stable configuration. So basically, we're shooting for 8. Octet. Any questions? Now, as we have talked about compounds, I've mentioned that there are 2 types we're going to deal with. Ionic, where we make charged atoms, and molecular, where we share electrons. Let's look at how we do a Lewis structure for sharing. Again, let's start with chlorine. If you isolate chlorine in the real world here, chlorine exists as Cl2. 2 chlorines bonded together. Why is that? Well, this is chlorine, it's group 7, right? 7 electrons. To make Cl2, what you do is you simply bring in another chlorine, like that. Now, if you look at it, we're sharing these 2 electrons between them. So this chlorine has 2, 4, 6, 8 electrons. It satisfies the octet rule. This chlorine, 2, 4, 6, 8 electrons. They both have 8 electrons. This is a shared pair of electrons. You count it for both. This is called a covalent bond. Covalent bond simply means there's shared electron pair. When you have a covalent bond, chemists will typically draw it as a dash. Your job is to simply remember, whenever you see a dash like this, what it really is telling you is that is an electron pair that's being shared. Each chlorine, 8 electrons, and they're happy. Well, let's go ahead and build a molecule. Ammonia. Ammonia is NH3. 1 nitrogen, 3 hydrogens. Nitrogen is in the middle, and is surrounded by our hydrogens. In order to draw a Lewis structure, what you want to do is find the atom, figure out how many valence electrons, put them around there, put the little dots, And then we want to make bonds. Remember, every bond can only have 2 electrons. Only have 2. So nitrogen is here in group 5. Hydrogen is group 1. What we're working with looks like this. Nitrogen in the middle with 5 little dots around it. 3 hydrogens with 1 electron each. Now we want to pair these up to make covalent bonds. As we look at this, right away it should strike you that, hey, here are 2 electrons. We could share those, right? We can share these. We can share these. So let's scooch everything together. When we do that, if you look at our nitrogen, how many electrons are around it? 8. We have satisfied the octet rule. And nitrogen is very happy. Now, how about hydrogen? Hydrogen is happy too, even though it doesn't have 8. Why is it happy with 2? Because where does it live? It lives here in the first period. It can only hold 2. It can't hold 8. It can only hold 2. If you put 2 electrons around a hydrogen, it's helium. Again, that's a group 8 element. If we draw this using our gashes, the way most people would, you would simply put 3 dashes around, and again, you would understand that each of these represents a pair of electrons that are being shared. In terms of common nomenclature, we refer to these guys as a simple single bond. Now, why do we call it a single bond, not just a bond? Because it turns out that covalent bonds can exist as single, double, or triple. Let's do an example here. Think about nitrogen itself. N2. Nitrogen exists as 2 nitrogen atoms bonded together. All right, so here we are, group 5. Draw 2 nitrogens, each with 5 electrons. You should have something like this. Now, our goal here is to come up with an octet of electrons around each nitrogen. And let's just see how we could do that. Here's our 2 nitrogens, right? Clearly, we could make a bond between these 2. So that's 1 bond. No problem there. Everyone agree with that? But if we did that, we would have 2, 4, 6 electrons around the nitrogen. That's not 8. So, remember, Lewis structures are just bookkeeping. They're just bookkeeping. So we could grab one of these guys and move it here in between. Grab one of these and do the same thing. Now, we have 2, 4, 6, 7 electrons around each nitrogen. If we do this again, we get this structure. How many electrons are around each nitrogen? 2, 4, 6, 8. This is our structure, and if you count it up, we have 6 shared electrons. So this nitrogen has 8 electrons. This one has 8 electrons. They both satisfy the octet rule. Now, what do we call this? How do we show this? Well, we have 3 covalent bonds, 3 separate bonds between these nitrogens. And so we would simply draw it this way and call that a triple bond. Any questions? Now on the exam, what are you going to have to do? What do you have to know? Oh, probably simple things like if you're looking at silicon, how many valence electrons are there? It's group 4. 4. Let's see. Probably you should be able to draw a simple Lewis structure like we just did for ammonia. If you can say methane, 1 carbon and 4 hydrogens. Carbon has 4 valence electrons, right? Each hydrogen would have 1 more, CH4. You would have 4 covalent bonds around the carbon. So simple stuff like that. We're not going to do anything really complicated or really fancy. Just make sure you understand the notion of sharing electrons to make covalent bonds. Here's methane, 1 carbon and 4 hydrogens. Again, the carbon has 4 valence electrons. Each hydrogen has 1. We wind up with 4 covalent bonds. Now, like I said before, compounds that have covalent bonds, we tend to call molecular compounds. That means we could call this a molecule. I thought, oh, maybe not. Maybe I added it this afternoon. But we've seen it before. The other type of compound is an ionic compound. Remember, we took our Lewis structures and we made ions by adding or subtracting electrons. This is sodium chloride. In sodium chloride, the sodium loses 1 electron to make sodium plus, and the chlorine picks it up to make Cl minus. So we're going to have 2 types of compounds. One is molecular, they're molecules, and one is ionic. They form these charged ions. Basically, in a molecular compound, you share electrons. In an ionic compound, you totally transfer them. We're going to, in the next chapter, learn how to recognize and name, right, chemical names for molecular and ionic compounds. First step, however, is to try to figure out how you can tell if a given compound, like methane, is going to be molecular or ionic. Well, it turns out that that's very, very simple. Remember when we talked about the periodic table, and I said about how colorful it was? Well, it's colorful because we classify things as metals, nonmetals, and semimetals. The very, very simple rule, it's a very simple rule. If your compound contains a metal, it will be ionic. If it only contains nonmetals and or semimetals, it will be molecular. So these guys, nonmetals and semimetals, will form covalent bonds. These guys, anything with a metal, anything with a blue guy, is going to be ionic. Very, very simple rule. The green guys here in the middle, these are our semimetals. Nonmetals and semimetals will form covalent bonds. Metals will be ionic. So, if you had a compound that was magnesium chloride, is that going to be molecular or ionic? What you want to do is simply look at your periodic table and find them. Magnesium is here in group 2. It's a metal. Chlorine is over here. It's a nonmetal. But if it contains a metal at all, that makes it not a molecular compound, and it will be ionic. Now, there are two types of nomenclature that you'll see here, depending on which book you look at. Some places will just simply call this ionic. Some places will be a little bit more technically correct, and call it not molecular. The not molecular pretty much translates to ionic, unless you're dealing with something weird. So, we'll call it not molecular, but remember, not molecular is the same as ionic. Hydrogen fluoride. Look at your periodic table and you simply find them. Hydrogen we know is over here in group 1, but remember, it's the only yellow thing in group 1, isn't it? So it's actually a nonmetal. Fluorine is here in group 7. It's a nonmetal. If we have two nonmetals, this is molecular, and these two will be joined by a covalent bond. Silicon tetrachloride. Step 1, you find your elements, right? Silicon is here. It's a green guy, isn't it? It's a semimetal. Chlorine is a nonmetal. semi-metal and a non-metal, covalent bond, molecular compounds. Sodium bromide. By now it should just jump out at you and scream at you and say, sodium, sodium's a metal, by gosh. If it's a metal, it's not going to be covalent, it's going to be an ionic compound and not molecular. Now this last one I just put in because I think it's cute. Remember we said chlorine exists as CO2, nitrogen is N2, whatever. Sulfur, it turns out, sulfur exists as S8. Are the bonds in S8 going to be covalent or ionic? Oh, really? All you have to do is find sulfur. It's yellow. Sulfur's actually yellow anyway. But it's a nonmetal. Because it's a nonmetal, all of these bonds will be covalent. It will be molecular. And this is what it looks like. It's kind of cute. It's a little crown. All right, what does this look like on an exam? Simple as it can be. Go ahead, run through the list, and simply label these as molecular or not molecular. Nickel chloride. Look at your periodic table, say, where the heck is nickel? Well, nickel's right there. It's a transition metal. Transition metal. If it's a metal, is it ionic or covalent? Well, it is not a molecular compound. Dihydrogen monosulfide. Hydrogen is here, it's a nonmetal. Sulfur is here, it's a nonmetal. This is molecular. Silicon tetrahydride. Silicon, semimetal. Hydrogen, nonmetal. Molecular compound. Sulfur trioxide. Sulfur, right here, it's yellow. You know that. Oxygen's right above it. It's a nonmetal too. These are covalent bonds. It is molecular. Calcium hydride. Calcium, oh my goodness, calcium's over here. It's a metal. Soon as you see a metal, what do you say? Not molecular. Do one more list. Cesium oxide. Cesium, where in the heck would that be? Gee, maybe down here. It's a metal. Soon as you see a metal, it is not a molecular compound. Ionic bonds. Diiodine heptaoxide. Oh my gosh. We'll learn next week how to name these things, but diiodine heptaoxide. Iodine is here. Oxygen is here. They're both yellow. This is a molecular compound. Oxygen difluoride. Oxygen, group 6. Fluorine is right next door. It's molecular. We've seen this guy before. I suppose technically you could call this carbon tetrahydride, but it's actually methane, the organic compound, natural gas. Carbon, oops, hydrogen, molecular compound. And finally, sodium chloride. Oh my gosh, how simple can you get? Sodium is a metal. This is not a molecular compound. All right. In this chapter, we have covered one additional tutorial. This is the electron structure. To be honest, a lot of people skip this one because they find it confusing. But if you can manage to work your way through it, and again, it tells you the answer if you get it wrong. If you work your way through it, it's 5 extra points. This certainly worth doing. The whole point of understanding electron structure is basically to get to the point where you can identify valence electrons by group. Once you know the number of valence electrons, you can draw a Lewis structure. And once you understand Lewis structures, you can easily differentiate between molecular and ionic compounds. So that's why we're here. Any questions? All right, I'm not sure what the lab is for Wednesday, but I will let you know. Lab number 3, whatever that is. And let's see. Our first exam comes after chapter 5. So one more time, the way this is going to work. We will finish chapter 5 just before spring break, actually. We will, when we finish chapter 5, I will give you a sample exam. Sample exam will look exactly like a real exam, except the whole question is different. You will work the sample exam, bring it in. We will go over it question by question. Make sure we understand everything. Following week, we will have the exam, and then I think it's spring break. So, you can all go out and fly. All right? Okay, have a good night.
Left my lab on my desk at work. Can I bring it on Wednesday?
Sure.
Okay.
I got a question.
Uh-huh.
Can you go into my tutorial and see the one that I did? Because I did majority of it, but I know when I emailed you, you didn't get all of it. But you checked it today or you got to email it to me?
Yeah, I have to check it. send me an email,
Okay.
just a regular email to my address, PYUIC.
All right.
And give me your name or whatever address you were using,
Okay.
and I will look and see how many I can find in the list.
All right. 'Cause I remember doing majority of it, but I'm gonna send you an email.
Okay, that's the best way to do it.